This video is brought to you by mywayteaching.com.
In this part, we are studying electrical energy part. Consider a conductor with the endpoints A and B in which a current I is flowing from A to B. So if you consider a conductor, then current is flowing from A to B, and the electric potential at A, it is denoted by V of A, and similarly the electric potential at B, we can represent it with V of B. Since current is flowing from A to B, V of A is greater than V of B. And the potential difference across AB is given by V, which is equal to V of A minus V of B. It is greater than 0. So in a time interval delta t, an amount of charge, that is delta q, which is equal to I into delta t, it travels from A to B, isn't it? And the potential energy of the charge at A, by definition, at A, if you consider the potential energy is Q V of A, and similarly at B it is Q V of B. So the change in the potential energy, we can write it as Q V of B minus V of A. The change in potential energy, that is, we can represent it with delta U pivot T, that is equal to minus delta Q into V. So we already know how to represent this delta Q. Here it is. So if you rewrite this, we'll get minus I V delta T. So if charges move without collisions through the conductor, their kinetic energy would also change so that the total energy is unchanged. Okay. Then conservation of total energy would imply this one, that is delta K is equal to minus U potential energy. So we can write delta K is equal to I V delta T greater than 0. Okay. So increased charges were moving freely through the conductor under the action of electric field. Then their kinetic energy would increase as they move. On the average, charge carriers do not move with acceleration but with a steady drift velocity. That is because of the collisions with ions and even with the atoms during this transit. And you know what happens during that collision? The energy which is gained by the charges, it is shared with atoms. So that atoms, they vibrate more vigorously. So the conductor heats up. That because of that only, in actual conductor, an amount of energy dissipated as heat in the conductor during the time interval delta t, it is given by delta W. Okay, the amount of heat energy which is dissipated during this process, it is delta W is equal to I V into delta T. So the energy dissipated per unit time is the power dissipated. That is P is equal to delta W by delta T. So we can say P is equal to IV. We know this equation. So using the Ohm's law, that is V is equal to I square, V is equal to I into R. If you substitute that one here, so we get one more equation, that is P is equal to I square into R, or in other words we can write like this also, V square by R. All these are the different ways as the power loss in a conductor of resistance R carrying a current I. So it is this power which heats up. For example, if the coil of an electric bulb to incandescent radiating out heat and light. That is one simple example. So where does that power come from? How that is possible? So here also we need an external source to keep a steady current through that conductor. So it is clearly this source which must supply this power. So in a simple circuit, as you can see in this one, it is the chemical energy of this cell which supplies this power for as long as it can. So this chemical energy of this cell supplies the power that is needed. So already we know the expression for power. In that we already saw that power is it is depending on the resistance R and even on the current through it and the voltage across it, isn't it? So this it has an important application even in the power transmission. Electrical power is transmitted from power stations to homes and even to factories, which may be hundreds of miles away via transmission cables, isn't it? So obviously one wants to minimize the power loss in that process of transmission. When they transmits through the cables, obviously power loss occurs. So we need to minimize it by connecting power stations to homes and factories. So how to do that? You just consider a device R to which a power P is to be delivered via transmission cables having a resistance RC. Okay. You just consider a device R to which power P is to be delivered via transmission cables having the resistance RC. If V is the voltage across this device R and I is the current through it, then we can write P is equal to VI. So the connecting wires from the power station to the device, it has a finite resistance RC. So the power dissipated in the connecting wires which wasted is PC. So that PC is equal to I square into RC, isn't it? So we can also write it as P square RC by V square. This P square, P, it is the for power for the device R. So to drive a device of power P, the power wasted in connecting wires is inversely proportional to V square. Okay. So, the transmission cables from power stations, they are hundreds of miles long, and even the resistance RC is considerable. So, to produce PC, these wires carry current at enormous values of V, and this is the reason for high voltage danger signs on transmission line. That is a common sight as we move away from populated areas. So using electricity at such voltages is not safe, and hence at the other end a device called a transformer, it lowers the voltage to a value suitable for use. So only we'll use devices called as transformers, because that much high voltage if you use, that is not at all safe, it is very much dangerous. So in order to reduce it voltage range to a lower level which is required for our use, we use these transformers in between. So these transformer will reduce the voltage level and then they will give the lower voltage to the for suitable uses. Okay. Now let us study about combination of resistors, series and parallel. See, the current through a single resistor R across which there is a potential difference V is given by Ohm's law, that is I is equal to V by R. So resistors are sometimes joined together and there are simple rules for calculation of equivalent resistance of such combination when they are simply joined together. See, a series combination of two resistors R1 and R2. So in this only, two resistors are said to be in series only when they are connected by end-to-end basis. As you can see, to the end of R1, R2 is connected. So when they are connected end-to-end, we say that these two resistors are connected in series. If a third resistor is joined with the series combination of the two, then all the three are said to be in series. So if you add one more resistance to this, then all these three are in series, isn't it? So you can see here, so a series combination of three resistors R1, R2 and R3. So here we can say all the resistors are connected in series. So only when they are connected on end-to-end basis. So to the end of one resistor, another resistor is connected. So to the end of R2, R3 is connected, isn't it? So then we will say that these resistors are connected in series. So by after this we can extend this definition to any number of resistors, isn't it? We will get the series combination. Then when we will say the resistors are connected in parallel, yes. See, when resistors are connected between the same 2 points, then we can call them as parallel. See, 2 or more resistors are said to be in parallel if one end of all resistors is joined together and similarly the other ends joined together. So, if one end of all resistors as well as the other end, which means if they are connected to two same in other words, we can say if they are connected to two same points, then we can say they are connected in parallel. So R1 is connected between the points here if A and B, and R2 is also connected to the same 2 points A and B. So then we can say the resistors R1 and R2 are in parallel connection, or we can say they are connected parallelly. So you can increase the number of resistors as we just saw in series R1, R2, R3. See, again this R1, R2 and R3, they are connected between the same 2 points. So there we can say they are connected in parallel. R1, R2 and R3 resistors are connected parallelly. So this is the difference between series and parallel combination.